Hello, welcome back to my YouTube channel. My name is Ego Suryakusuma, and my college number is 21055531063. And today we're gonna discuss about metal forming processes, and let's get to the topic. Before we go to the topic, I want to mention my sources. Is from Handbook of Manufacturing Process, How Products, Components and Materials Are Made by James G. Brala, and I take another source from journal from Google. In today's video, we're gonna discuss 4 topics. The first one is sewing. The second one is flame cutting or thermal cutting. The third one is electrical machining processes. The fourth one is finished machining operations. Okay, we'll go to the first topic, which is sewing. The sewing is the parting of material through the use of narrow cutter, a saw, which contains a series of cutting edge that pass against the work accuracy and excellent surface finish. The operation is rapid and particularly suited to mass production conditions. So this operation skill requirement are not high because the neat precision is incorporated into broaching tool. However, broaches are expensive, and this is why broaching is chiefly found in mass production situations where the tooling cost can be amortized. So, however, some internal shapes are not practical to machine by other methods, and that is why broaching is commonly used for keyways and split shape holes, dovetail slots, and fire 3 shaped slots for turbine blades. So the equipment it requires for broaching range from simple arbor presser for keyway broaching to huge special machine used in the automotive industry for surface machining engine blocks and other large components. So holes as small as 1.3 mm and surface as large as 0.5 mm wide, and having continuous or reciprocating motion. Okay, in sewing, we got the first subtopic from sewing is circular sewing, which is used a saw in the form of circular disc with cutting teeth on the periphery. As the circular saw rotates, it is rubbed against the workpiece, machining a narrow slot in the workpiece and eventually severing it. So circular saws for metal cutting are sometimes called cold saws because they don't significantly heat the workpiece as friction saws do. So they often have insert cutter teeth of carbide rather than teeth form of the blade material, or have cutter segment fastened to a center disc. So blades are sometimes large in diameter to permit the sewing of bulky workpiece. So curves are considerably wider than those on band or hack saws because the circular blade must be thick enough to provide rigidity. So accurate and smooth cut surface are feasible with this method. The circular saw process is used to make blanks for subsequent operation or to cut structural members to the desired length. So the second topic from sewing is band sewing. It is most commonly a cut-off operation instead of circular disc. The saw is an endless steel band with cutting teeth on one edge. So the blade moves as it cuts in one direction. So cutting is continuous, and blade wear is uniform over the whole length of the blade. So since the blade is normally thin, little material is lost to chip. Waste and power requirement are modest. So the workpiece or the blade can be fed manually or mechanically. So for cutting off, the blade is normally horizontal and is fed mechanically or by gravity. So band saws are also used to contour sewing, and band sewing is suitable for thin walled tubing and other somewhat fragile parts because cutting forces are lower than with other sewing processes. Okay, The third subtopic from sewing is contour sewing, which is a band saw. The power band normally moves vertically downward, and the workpiece resting on a horizontal table is fed into the moving blade either manually with or without power assist, or automatically into the moving blade. So the cut can be in a straight line or a curved path, depending on the stage of the part to be produced. Contour work is not uncommon in tool shops for straight line or curved path. So template cams, dies, and fixtures flat stock is the most common shape cut by this method, but material of other shape is also precise. A quantity of parts of thinner material can be cut in one operation by stacking a number of blank sheets. So the fourth subtopic from sewing is hack sewing, which is use a reciprocating saw, either manually or mechanically operate, to perform a cut-off operation. So cutting takes place only on the forward stroke. Feed of the blade is commonly by gravity, but hydraulic and other mechanical feeds are often used on production hack saws. So production hack saws also incorporate a rapid return stroke to minimize the cutting time. So the short straight blade is less expensive than a band saw or circle saw blade, but the cutting is less rapid. So once low power hacksaw machine complete the operation automatically, stopping when a limit switch is tripped. So blade and equipment are less costly than those used with other sewing methods. So we're going to the fifth subtopic from sewing, which is abrasive sewing, and uses a circular band or reciprocating saw blade with a cutting edge that consists of abrasive particles rather than teeth form in the edge of the metal blade itself. Thin circular cutters of bond abrasive are most common, so surface speeds are much higher than with conventional sewing. Abrasive sewing is used when the workpiece material is hard or otherwise difficult to cut with metal cutting teeth. So hot metal builds are cut with this method. Cutting is quite rapid with large wheel, high horsepower machine, so coolant may be used to improve the finish of the cut surface, reduce burrs, and minimize heat effects. Smaller machines are usually operated manually, and equipment costs are low for this approach, but the wheel cost is high compared with other sewing methods. Okay, so the sixth subtopic from sewing is diamond edge sewing, which is a kind of abrasive sewing that uses diamond abrasive particle because of particular hardness of the workpiece material. So cutting of ceramics, glass, stone, carbide, hardened die steel, nickel, and cobalt alloys are typical applications. Sufficient coolant and accurate feed control are necessary. Okay, the seventh subtopic from sewing is friction sewing, which is use an extremely high-speed saw blade that softens and melts the workpiece material with friction heat. So the cutting teeth then remove the softened material with a cutting action. Either a band saw or large circle saw is used. So the movement of the blade prevents it from overheating, since any one part of it is in contact with the hot work for only an instant. So however, the blade may also be water cooled. The blade is heavier and not necessarily as sharp as conventional blade. So the process is suitable for hard materials like Rockwell C42 or more, which cannot be cut well with conventional sewing. Material ejection to the curve is heat affected. The method is slightly less accurate and has a poorer surface finish than that produced by other sewing methods. So copper, aluminum, and cast iron are not suitable for the process. Okay, now we're going to the second topic from the video. The second topic is flame cutting or thermal cutting, which is flame cutting involves one of two underlying processes. The first one is severing or cutting of metal piece by melting a narrow slit. The second is severing or cutting by chemical action, wherein the metal oxidized at high heat. The variety of method used is discussed below. Flame cutting is most widely used for cutting heavy plate as thick as 75 centimeter, and structural shape and sheet where tolerances are not so strict. So the cutting torch is often manually guided, especially in field work or when tolerance can be liberal. However, the flame cutting machine guides the torch more accurately along straight lines or curved paths. A template tracing, optical tracing, or part drawings, numerical or computer numerical control are methods used to guide the torch. Tip along whatever path is required to cut the desired workpiece from the stock to be cut. So the process is the most often used to cut parts from flat stock. However, workpiece of many other shapes can be cut with this process. It is also commonly used in dismantling various structures or equipment. So most flame cutting torch can be portable, so field dismantling is quite feasible. Okay, now we're going to the first subtopic from flame cutting and thermal cutting, which is oxy-fuel gas cutting, or OFC, which is used acetylene, natural gas, propane, or hydrogen in combination with oxygen to fuel the process. With various metals, a small area of the workpiece to be cut the first broke to temperature of about 870 Celsius with a flame or pure gas or oxygen mixture. When the metal reaches the proper temperature, oxygen is added to the fuel mixture and the workpiece metal in a narrow section is oxidized or burned with the aid of the oxygen. Iron oxide is in liquid form, is generated and is blown away from the workpiece by the force of the gas stream exiting the torch nozzle. As the torch moves, a narrow steel slit is made the workpiece. So with a non-ferrous metal, oxidizing may not take place, and the metal removed by simple melting. So the torch is commonly held and controlled manually, and particularly for work not requiring great dimensional accuracy, but mechanically held, touch controlled by templates, optical tracing, or computer numerical control are also used. The process works best with carbon and low alloy steel, and a typical cutting speed for 225 mm thick steel plate is 0.46 meter per minute. When cutting stainless steel, metal powders or chemical additives are incorporate the stream to improve the cutting action. So some machines have multiple torches and can put a number of parts from one piece of sheet or plate material at the same time. Part the most commonly cut from for flat plate and material from 1/8 to 60 inch in thickness can be cut. So shipbuilding, construction, tank, pressure vessel, and heavy equipment manufacturer are included twice. Then use the process, and it is illustrated as you can see in the pictures up. And welding is common subject operation there, and there is heat affected zone advanced to the cut in the right, and can be adverse effect with the some materials and application. Okay, now is metal powder cutting, or PLC, is a method applicable to metals that do not flame cut very easily. Preheat iron powder is injected into the flame to raise the cutting temperature. Oxidation of the iron provides an aid to cutting metals that are highly resistant to oxidation. Chromium, nickel, stainless steels, high alloy steels, and cast iron are cut with this method. It is also used to remove gates and risers from iron and stainless steel castings, and to cut stack, sheet, or plates more easily. So the third subtopic from flame cutting was chemical flux cutting. It adds flux to the cutting gases to make the metal oxide more fluid and more easily removed from the gap of the cut. Power chemicals such as sodium carbonate and other salts of sodium are used. The process is sometimes called flux injection and is used to relative minor. So the fourth subtopic from flame cutting, which arch cutting, which involves a group of processes that use the heat of an arch to melt a metal workpiece to sever it or remove metal, and all common arch welding process, and can be adapted to metal cutting as well as metal fusion. When arch processes are used to cut steel and other easily oxidized metals, oxygen may be used in conjunction with the arch to support the oxidation. In metals that do not oxidize, the cutting action is mainly from pure melting, and air or a shielding gas is used to provide the force needed to help expel the molten metal from the gap. So the most significant process the group are plasma arch cutting, air carbon arch cutting, and oxygen arch cutting, which is oxygen lens cutting, and gas metal arch cutting, gas tungsten arch cutting, shield metal arch cutting, and carbon arch cutting are other arch cutting processes that are not widely used in industrial production situation. Okay, now we're going to the subtopic from cutting edge of flame cutting, which is a plasma arch cutting. It uses extremely high temperature, is 11,000 to 28,000 Celsius of the plasma arch to melt the workpiece metal. So severing is a result of melting rather than oxidation, and a direct current arch between a tungsten electrode and torch body creates the required high temperature and partially ionized a stream or of nitrogen, hydrogen, argon, air, or a mixture thereof. Partially ionized gas are mixture positive charge ions, free electrons and neutral atoms as the stream's gas of leaves the nozzle. The separate electrons are combined with the gas atoms and release additional energy. The constricting effect of the nozzle further increase the arch temperature, which is and quickly heats and melts the workpiece metal. A shielding gas is often used to protect the ionized stream. Sometimes a surrounding stream of water is also used to help confine the stream so that the melting takes the place is only a narrow curve. So the force of the stream, the shielding gas and water all expel the metal from the cut. So the process provides very high cutting speed, 4 to 5 times higher than those achievable with a standard oxy-fuel cutting. It works equally well with metals that do not oxidize because melting rather than oxidation is the means and by which the metal is removed. There is a heat effect zone but is narrower than the resulting from the oxy-fuel gas cutting. A stainless steel and aluminum are major application for the process, although melt and alloy steel, titanium, bronze, copper, and magnesium are also proceed. Smooth cuts in plates up to about 150 mm thick are feasible. Dutch work over the road tanks of aluminum or stainless steel, which is the food and chemical processing equipment, ships and barges are all manufactured with the use of this process. Okay, now is the fourth subtopic from arch cutting. And second subtopic from arch cutting, which is air carbon arch cutting and grooving. So in this process, we can see at the picture below, intense the heat from the electric arc between the tip of the carbon electrode and the metal workpiece material. A high velocity air stream passing through the arch blows the molten metal away from the area of the cut. So through it can be used for through cutting, and the method is commonly used for gouging, an application not feasible with oxy-fuel gas cutting. So when used for gouging, it leaves a clean groove. One common application is the preparation of a square edge plate for welding. So another is to remove defective welds so that the joint can be reworked. So the process is also used to remove screws, runner risers, and fins from castings. Cast iron, steel, stainless steel, this ductile and malleable iron, nickel, aluminum, copper alloys, and other non-ferrous metals have been processed with this method. Equipment is simple, but the operation is noisy and the scattering of molten metal may be a problem. Okay, now we're going to the third subtopic from arch cutting, which is oxygen lens cutting, or OLC, also known as oxygen arch cutting. Is used to steel mills to serve material that is already hot from the steel making process. A small pipe or lens carries oxygen to the workpiece, which is hot enough to start the oxidizing reaction without the need for further heating by fuel. The heat generated by the oxidation combined with the oxygen flow from the pipe are sufficient to continue the oxidizing reaction and oxide removal until cutting is complete. So the lens is usually a simple length of pipe or tubing with a diameter of 3 to 6 mm and coated with a non-conductive material and connected to a valve oxygen supply hose. The lens is consumed as the operation proceeds. When cool workpieces are to be cut, the surface of the metal is heated with a separate torch to temperature high enough to start the oxidation reaction with the oxygen lens. The operation can be performed underwater. In some process variation, aluminum or magnesium wire in the lens develops additional heat of oxidation, enabling the lens to cut concentrate, bricks, and other non-metal objects. Okay, now we're going to the fourth subtopic from arch cutting, which is gas metal arch cutting. It's a metal cutting version of GMAW, gas metal arch welding. In both process, the heat is provided by an electrical arch between the workpiece and continuously fed metal wire shielded by the flow of an insert shielding gas. In the case of metal arch cutting, the purpose of the operation is to serve parts of the workpiece rather than to fuse it to another part. The molten metal is evacuated from the area of the cut by the combination of the force of the shielding gas, the arch, and the vapor pressures from materials vaporized by the arch. So this method is not highly significant in industrial production situation. Okay, now we're going to the fifth subtopic from arch cutting, which is gas tungsten arch cutting. It's the cut variation of GTAW, gas tungsten arch welding for cutting higher amperage and increased shielding gas flow are employed. The arch melts workpiece metal, which is a force of the cut by gas pressure from the shielding gas and the effect of the arch. Gas tungsten arch cutting is used for cutting stainless steel and various non-ferrous metal, including aluminum, copper, nickel, magnesium, silicon, bronze, and copper nickel. An argon hydrogen gas mixture is commonly used, as with gas metal cutting. This method is not widely used in production situation. The sixth subtopic from arch cutting is shielded metal arch cutting. It's similar to stick welding, and that method is used to cut the workpiece rather than to fuse it to another member. A metal electrode inrod from coat with a flux is used without any gas jet or blank. The heat of the arch of high current density melts the workpiece, and gravity is used to carry away the molten metal. So this method is limited to situation where it is in convention to use more effective flame cutting methods. Okay, now the seventh subtopic from arch cutting is carbon arch cutting. It's not significant in industrial process, but is found in small shops that lacks more sophisticated equipment. The arch between the carbon graphite electrode and the workpiece melts the workpiece where the arch contact it. So gravity and pressure of the arch rather than the air jet used with air carbon arch cutting remove the molten metal. Okay, now is the fifth subtopic from flame cutting is laser cutting, which is laser cutting is mainly a thermal process in which a focused laser beam is used to melt material in a localized area. A coaxial gas jet is used to eject the molten materials and create a curve. So a continuous cut is produced by moving the laser beam or workpiece under CNC control. There are three major varieties of laser cutting: fusion cutting, flame cutting, and remote cutting. In fusion cutting, an inert gas, typically nitrogen, is used to expel molten material out of the curve. Nitrogen gas does not exothermically react with the molten material and thus does not contribute to the energy input. Okay, now we're going to the third topic from this video, which is electrical machining processes. The first one, we get into the first subtopic from it, is electrical discharge machining, or EDM. So it's sometimes called spark erosion machining and is used to series of fine electrical discharge of spark to erode the workpiece material. So the discharge passes from the tool cathode to the workpiece anode at a rate greater than 20,000 times per second. The workpiece material, which must be electrically conductive, melts or vaporizes at the point where it is touched by a spark. So the electric fluid, usually kerosene, circulates between the electrode and the works. The fluid conveys the spark, cools, and it flies some molten materials and carries away the residue. So the process is advantageous for hard conductive material, including the hardened steel and carbide. So this is no significant cutting force, so delicate shape can be produced. The gap between the node and the work is only about 0.05 millimeter, and is servo controlled. There is an overcut equivalent to the length of the spark from the electrode to the work. The cutting rate is slow compared with the conventional machining, but is still advantageous for materials too hard or otherwise not easily machined. The rate cutting when surface finish are controllable by varying the frequency, voltage, and a current in the electrical pulses. High energy levels in the pulses produce faster erosion for the workpiece but rougher surface finish. Typically, the rate of cutting is reduced towards the end of the operation in order to provide smoother surface. So spark erosion produce small craters in the workpiece, and these craters are manifested as a matte finish on the workpiece. So the tool also seen some sparks action in the reverse direction. Additionally, some secondary operation may be required to remove a hard thin recast surface layer or fine surface cracks caused by thermal stresses, depending on the material used and the function of the part produced. So we're going to the first subtopic from EDM, which is RAM EDM, which is sometimes called die-sinker EDM. The electrode is shaped to fit the desired cavity and is fed into the workpiece, which is eroded and to match the electrode shape. The electrode is made undersized to allow for the expect of a cut, commonly 0.0113 to 0.5 millimeter, and feed is downward into the work. But CNC control can also provide transverse movement of the electrode to produce special shapes in the cavity. So since the tool also erodes and becomes tapered, extra tools are more often made. Graphite is a commonly electrode material, but copper, brass, aluminium, copper, tungsten, zirconium, and other alloys are also used. So the process is mainly used to machine cavities in hard steel dies and molds. It is also used in machining carbide and in salvaging hard added parts or tools such as broken tops, slots, non-round holes, small deep holes, and machining of honeycomb, and other fragile parts are additional applications. Okay, the second subtopic from EDM is wire EDM. We just use a constantly moving wire instead of the sharp electrode. The wire of is 0.025 to 0.33 mm diameter, passes through the work with the vertical axis. Thread may be set to an angle when required when cutting apertures for staple tools. So tungsten, copper, and brass are common wire materials. The wire of the work is fed horizontally as the cut progresses. To cut a slit or shape through hole in a workpiece, different wire materials is constantly exposed to the spark. So wear of the wire is widely distributed and is not a problem. So the process is often used to cut die openings is hard and stocks to produce dies and die component. A high level of accuracy and fine detail can be achieved. So now we're going to the second subtopic from the third subtopic from EDM, which is electrical discharge grinding, or EDG, which is similar to electrical discharge machining, except that the electrode is a rotating wheel instead of the electrode that is stationary except for the down feed. The workpiece and the wheel are immersed in dielectric fluid, and metal is removed by the same kind of spark erosion as that which occurs with EDM. The wiping action of the wheel produce better surface finish than with ram type EDM. So the graphite wheel is dressed as necessary to compensate for its wear in the process. The volume of material lost by the wheel from were average about 1/3 of that removed from the workpiece, but is considerably less in many instances. So since the wheel wear is spread over its circumference, the amount of reduction of wheel diameter from this dressing is normally small. The process is used to in shaping carbide from tools and in grinding fragile of brittle materials. So material be ground by EDG must be electrically conductive. There is a thin heat effect right from the process. So the layer parity is from 0.0025 to 0.038 mm in depth. Okay, now we're going to the fourth subtopic from EDM. Is electrochemical machining, or ECM. It is remove metal by a reverse electroplating process. The workpiece becomes the anode, and the tool is the cathode of the electrolytic process. A highly conductive electrolytic fluid is pumped into the space between the workpiece and the tool. The high amperage current removes workpiece and material by anodic dissolution. So the workpiece takes a mirror image shape of the tool. The gap between the electrode tool is a workpiece as small as 0.025 mm, and pressure of electrolyte must be high to ensure adequate flow. The temperature control of the electrolyte is control of the gap and feed rate of the tool, and the maintenance of the electrolyte is an important element in the process. The electrolyte is circuited through equipment that removes the operation debris from the fluid. The process is particularly suited at hard materials and other that difficult to machine by conventional method. So workpiece hardness does not affect its machinability by the process, but the workpiece material must be electrically conductive. The tool does not wear and no stresses are included in the workpiece by the operation. So common tool materials are copper, brass, bronze, stainless steel, and the copper tungsten. Just like metal removal rates are good compared to a number of other non-traditional machining process and average to 1 in 3 or 16 centimeter 3 per minute per 10,000 amperes of current. So the process is used for die sinking. Manufacturer of jet engine parts can profile and machine of small deep hole. So ECM is the most advantage for materials that are difficult to machine by conventional method. Now we're going to the first subtopic from electrochemical grinding or ECG, which is similar to electrochemical machining but will replace the relative stationary tool with a rotating conductive grinding wheel. So this wheel normally consists of an aluminum oxide abrasive bonded to a metal wheel, which acts the cathode of the electrolytic circuit. Electrolytic fluid circulates in the area where the abrasive contacts the work. The combination of the electrolyte and mechanical action remove material from the workpiece, but the electrolytic action predominates, accounting for about 90% of metal removal. Anodic dissolution of the workpiece metal leaves surface metal oxide. In conventional ECM, the fusing action of the electrolyte removes this oxide. In electrochemical grinding, the abrasive mainly functions to remove the oxide film, exposing a new metal surface of the electrolyte. So the abrasive also separates the metal wheel from the work, preserving a fine 0.001 or 0.025 mm gap between the two. It also carries the electrolyte solution to the gap. The process has the advantage of relatively high metal removal rates for hard metals, freedom from heat damage to the workpiece, and the ability to grind fragile parts. And the plunge, surface cylindrical, and internal grinding are all feasible with the process. However, the capital costs are high and the electrolyte can be corrosive for the equipment and workpiece. The process is commonly used to sharpening carbide cutting tools, avoiding the high wear rates, expensive diamond abrasive wheels that will otherwise be required. It is also used to grinding surgical needles, honeycomb structures, and other fragile parts. Okay, now we're going to the second subtopic from ECM, which is electrochemical turning or ECT, and its other application of electrochemical machining. The workpiece rotates as in conventional turning, but the cutting tool is replaced by the electrode, and the electrolyte fluid is direct to the gap between the tool and the work. So material is removed by electrolytic action between the workpiece anode and the electrode cathode. So facing and turning cuts can be made. Disc forgings and bearing rays are machined by the process. So we're going to the third subtopic from electrical machining processes is electrochemical discharge grinding or ECDG. So it's sometimes called electrochemical discharge machining. It is a combination of electrochemical grinding (ECG) and electro discharge grinding or EDG. Stock removal are primarily by ECG but oxide from ECG are then removed by an intermittent spark discharge instead of by abrasive particle. So the wheel is conductive, normally made by graphite, and has no added abrasive. The fluid used in highly conductive electrolyte by contrast with EDG, which use the electric fluid. The wheel rotates rapidly 4,000 to 6,000 feet per minute to 12,000 to 1,200 to 1,800 meter per minute. So bringing fast electrolyte between the workpiece, the anode, and the wheel, the cathode. Sparks discharge occur randomly when the breakdown voltage of the oxide film is exceeded. So alternating current or pulsating direct current are used. Current density ties are less than in ECG or to avoid cratering of the workpiece and wheel. And metal removal rates are considerably slower. However, the wheel cost for the graphite-only wheels is less than the required for abrasive wheels used with ECG. So the process is used to grinding of carbide cutters in cap, and it can also be used with hardened tool. Streets, nickels, alloy, and parts are heat sensitive or fragile, such as tiny column and other fragile parts are advantageous because they are finish free from burrs, and streets from grinding can be used if the wheel has a profile. Now we're going to the fourth subtopic from electrical machining processes, which is electrochemical honing, or ECH. Is electrolyte action added to conventional honing and is quite similar to electrochemical grinding. So material is removed from the workpiece by a combination of electrolyte action and mechanical abrasion. The electrolyte action removes most of the material. The abrasive action of the honing stones remove the oxide produced by the electrolyte action. So the equipment provides both reciprocating and rotational movement of the honing stones, as in conventional honing. However, electrolyte fluid handling is added, and the tool that holds the honing stones is hollow, and fluid passes from the tool into the gap between the stones and the workpiece. So the gap between the tool and the work is approximately 0.003 or 0.005 inch or 0.08 to 0.13 millimeter at the start of the operation, increasing to about 0.5 millimeter at the conclusion, but the stones remain and contained with the workpiece normally. The surface of machine hole, so the wedging action of the conical piece and the tool force the stones outward as the honing takes place. The operation provides metal removal 3 or 5 times as fast as regular honing, while the wear of the honing stone is considerably less. So the burring action is also superior, and the work is more apt to be free from stressing fluids or heat damage. So, however, the operation requires the complex equipment due to the need of control by electrolyte action and the corrosiveness of the electrolyte. Therefore, is not necessarily more economical than conventional honing. The process is used to refine the bores and harden parts such as gears and pump components, particularly when production quantities are large. Now we're going to the fifth subtopic from electrical machining processes. It's electro-etching, or ECH. So it's method for marking workpieces that are electrically conductive. A stencil is placed on the workpiece and a pad containing an electrolyte is placed a dab on the stencil. The workpiece and the pad are connected to a source of direct electrical current. So the current can remove workpiece material through electrolyte Kelly in the areas corresponding to openings. Stencil. So the method is useful for placing the identification markings on metal with fairly smooth surface. Electro etching is normally performed manually and is suitable method when production quantities are modest. Okay, now we're going to the fourth topic from this video is finished machining operation. We're going the first one subtopic is honing, which is a low velocity abrasive machining process on or more bonded abrasive stone or sticks are put in area contact with the surface to be machined. So in contrast with grinding process where the abrasive and the work are in contact essentially on a line. Slow movement of the sticks in several directions abrades the high spots on the workpiece surface and makes the surface smoother than more through. So with greater dimensional and geometrical accuracy, because of the slow movement, there are no heat effect to the metal surface. So removes only a small amount of metal less than 0.13 millimeter to but improve the dimensional accuracy and surface finish of the surface being honed. The operation can be performed by hand, but for production situation, a machine that impact reciprocating motion in several directions of combined reciprocating and rotary motion are used. Cutting fluids are normally employed. The most common application is the finish machining of bored holes to remove tool marks. Wave finish or taper, the stones are allowed to float and follow the direction of the hole's axis. The cylinder walls of internal combustion engines are typically finished by honing, which is the gear teeth and bearing rays are also honed. Okay, now we're going to the second subtopic from finish machining operation, which is lapping. So another low velocity abrasive machining process is utilize a fine abrasive in paste or powder foam, which is contained between the workpiece and the lapping tool. So the lapping tool is made of material softer than the workpiece and is shaped to mate with the surface with being machined. It has the function of holding the abrasive, so random reciprocating motion of the lap and the abrasive with the light pressure applied. Refine the dimensions and the smoothness of the workpiece surface to close tolerance. Unlike honing, the motion is not necessarily in more than one direction, so very little material is removed, so seldom as much as 0.025 mm, and the purpose is remove fine scratch marks or create very flat or otherwise smooth and precise surface. So the process is also used to provide a very close fit between the mating surface, flat cylindrical or spherical surface of those of special shape can be processed with this method. The operation can be performed by hand with a machine designed for the purpose. In some cases, abrasive coat, pepper, bone abrasive, or cloth clamps are used. The relative motion between the lap and the workpiece is always low. Typical applications are finishing of gauge block, plug gauge, ball bearing races, valve seats, roller bearings, and optical parts. And parts requiring metal-to-metal sealing surface are frequently lapped. Okay, now is finish machining operation. The third subtopic is super finishing. The third is a third low velocity surface refinement process. A solid abrasive is used, but is loosely bound so that it wears the shape of the workpiece surface. Thus, a large surface area is in contact with this abrasive at all times during operation. Control a bi-directional movement of the workpiece and the abrasive until light pressure removes high spots and smooths the surface. Removing surface material that has been smeared or dissolved by prior grinding or machining. Typical speeds of movement between the work and abrasive is 12 to 50 feet, 4 to 15 mm. Per minute pressure is 70 to 275 kPa. A liberal amount of oil-based cutting fluid normally accompanies the operation, typically about 0.005 to 0.025 mm. The material is removed, so mineral-like surface finish can be produced. So the process we just use smooth, flat, curved, or spherical bearing surface automated. Crank hands, camshaft, bearings, brake drums, and distributor shaft are typical super finished parts. Okay, now we're going to the fourth subtopic from finishing machining operation is burnishing. So burnishing is a means of smoothing machine or other surface by rubbing a smooth, hard object against the surface with considerable pressure. So burnishing is not machining operation. No workpiece material is removed, but instead it forms and presses down localized high spores from cutting tools, and there be smooth, rough areas. So we're going to the last subtopic from finished machining operation is roller burnishing. So refines the surface of workpiece by pressure rolling rather than by removing metal. So the burnishing tool incorporates one or more hardened, finely polished rollers which bear against the workpiece at high pressure. each one are achieved by the desired effect by deforming the surface material of the workpiece as it rolls against it, compressing the minute peaks of the surface roughness into the valleys. The force applied to the burnishing tool depends on the amount of the pressure required to exceed the yield point of the workpiece material. So multiple rolls may be used depending on the shape of the surface being roll burnished. Gear tooth finishing, one common burnishing operation performed by rolling the gear workpiece against 3 smooth, hardened burnishing gears. So compressive stresses left in the surface after operation and surface work hardening improve resistance to wear the fatigue failure. The process limited the workpiece up to about Rockwell 40C in hardness and with walls thick enough to withstand the force involved. Roller burnishing is holes can be substituted for a supplement to rimming and boring, and the typical parts that undergo the operation are cylinder bores, valve streams, piston rods, turbine shafts, pump plungers, and rolls for the plastic and paper industries. So that's all for my video. Thank you for watching and see you guys in the next video. Bye bye.